The Globe's Report on Business wants to hear from you. Do you know an organization that's a change maker? One that's taking on the social problems Canadians are facing, from climate change to racial discrimination to income inequality. If you know a business that's working to better their industry and the world around them, you can nominate them today at tgam.ca/changemakers. The deadline is October 20th. Let's just start with the scene in Utah, because I know you were there when the Osiris-REx capsule actually returned back to Earth. So can you describe what was that like?
I was there, and this is an assignment I was really looking forward to. It's a kind of mixture of excitement and anxiety. I would call this a genuine event.
The Globe's science reporter, Ivan Semeniuk, recently got back from the Utah desert. He was there to witness the return of a space capsule that carried part of an asteroid more than 4 billion years old.
This is sometimes happens in space science where, in this case, you've got a capsule coming into Earth. Once they made the decision for the main spacecraft to release the capsule, that's it. It's coming. You know it's coming. The only thing you don't know is what's going to happen next.
The return is especially tricky because of the speed.
It's coming in from a solar orbit, hitting the atmosphere at 12 kilometers per second. And high altitude aircraft could, kind of got a picture of it coming in. It came in like a bright hot meteor and then cooled down. And you see this thing falling. And of course, we know as the time is counting down that any minute the parachute's supposed to open.
Our next milestone, we should be expecting main parachute deployment at around 8:49 a.m. Mountain Time. That will be at around 5,000 feet elevation.
At the moment that the first parachute was supposed to come out, we didn't see it. And then I think there was just dead silence in the press room. There was that sense that maybe this is not going to go as we plan.
We continue to track with our high altitude camera here.
And then suddenly the main parachute opened.
EDO milestone, we have confirmed parachute deployment.
Wow, and after an exhilarating streak across Earth's atmosphere, we have parachute deployment. You can see just a sigh of relief from the team. I can hear some applause here. There is that orange creamsicle colored parachute.
So then you knew that this thing was going to be in the clear, and then it was kind of drifting down on the parachute, and it landed beautifully.
EDO milestone, we have touchdown. I repeat, EDO. FRC has touchdown.
And actually, in the press conference afterwards, the principal investigator, Dante Loretta, admitted that when that parachute opened, he burst into tears. After 7 years of flying in space, 20 years of planning, and $1.6 billion, there was a lot on the line. So it's good news that it came in the way it did.
There was a lot on the line with the Osiris-REx mission. But now we have bits of an asteroid on Earth. So today, Ivan will tell us what this asteroid might teach us about the beginnings of our solar system, and maybe even the origins of life. I'm Menaka Raman-Wilms, and this is The Decibel from the Globe and Mail. Ivan, thank you so much for being here.
Oh, my pleasure.
So over the past 60 years, we've seen a number of spacecraft heading out into space, but there seems to be a particular amount of excitement around this Osiris-REx mission. So, Ivan, what makes it so special?
Sure, I would sort of put it in terms of, or sort of rank levels of excitement. And we have, you're right, over the last 60 years, there have been innumerable missions to the planets now, it seems. Hard to keep track of them all. I would say the first level of excitement is seeing a world, a planet, or a smaller body for the first time up close. Those first pictures from space as it's flying by. That's exciting. Then even more exciting is to land on another world, like landing on Mars, landing on Titan, a moon of Saturn. These were incredible moments. But I think an even higher level of excitement is this idea of bringing something back, getting a piece of another world and bringing it back to Earth where it can be studied in detail with all of the equipment, all of the techniques that are available, and future techniques that might still be developed. That's only happened a very limited amount of times. And for the United States, it's the first time they've ever brought anything back from beyond the moon. And for Canada, which is a part of the mission, it is actually the first time Canada will take possession of some kind of extraterrestrial material that came from another place. This is a first for Canada.
Okay, and we're going to get into Canada's involvement as well. I just want to come back to, like, on a high level here, Ivan, what are scientists actually hoping to learn from this mission and from the samples that we brought back?
Well, asteroids are very small objects. This one in particular is only about 500 meters across, but they allow scientists to ask some really big questions. And in this case, I think the biggest question is, how did our solar system form? What are the raw materials that it formed from? There are many different kinds of asteroids. Some of them have, when the solar system formed, the basic idea is that you had the early sun surrounded by a swirl of debris, dust, and gas, and gravity allowed that material to kind of coalesce into larger objects. So some of those objects would have become the asteroids that we see today, and they're actually leftovers from other objects that were swept up into creating the planets, for example.
So this could give us kind of an early look at our own solar system then, essentially.
It's really looking at the building blocks. But this kind of asteroid, the one that it's called Bennu, the one that was visited by the Osiris-REx mission, it's a much more primitive body. It was never really melted. It's very carbon rich. So it has some of the ingredients that are probably important for how Earth came to be the way it is, how it came to be a planet that can support life. It's also, I think, the kind of asteroid that would have probably a fair bit of water locked into the minerals.
Oh, wow.
Not liquid water on the surface, but there's water, kind of chemically inside the rock, inside the material. And all of that gives clues to how Earth got its oceans, how Earth got started to be the world it is today.
Okay, so it sounds like the main reason for this mission is to give us this look back into the early development of our solar system. But Ivan, I know there's also some other reasons for doing this, including the fact that this asteroid could potentially get close to the Earth. I know the chances of it hitting the Earth are very low, but still there is a chance, right? So how could this help us on that front?
Sure. This is an asteroid that started in the asteroid belt, out beyond the orbit of Mars, but now it orbits much closer to Earth. So other reasons for doing this kind of mission are to study basically the physical structure of asteroids, to understand if sometime in the future we need to move or adjust the orbit of an asteroid to prevent it from hitting Earth. That's a small possibility, but one with very high consequences.
Can I just ask you one question on that, though? Like, how does us knowing what the asteroid is made of actually help us defend ourselves? Like, what would that do?
It has to do, imagine how there's a big difference, for example, between an object that would be solid all the way through. Say you're pushing on something that's solid, like a book or a box or something like that. Or now imagine you're pushing on a feather pillow that's very fluffy. If you push on the pillow, you might not really move it very much. You're just kind of pushing your hand into the pillow, as opposed to kind of moving it. So understanding that larger structure, but also understanding the thermal properties. This is a little more subtle, but the sun affects asteroids. They take in the heat of the sun. They absorb the light of the asteroids. They re-radiate it as heat. That small amount of kind of taking in energy, releasing solar energy, actually can adjust their orbits a little bit or cause them to move a little bit. It's almost like an extra bit of propulsion. But to understand that, you have to know the thermal properties of the asteroid. So in a way, measuring the properties of this asteroid very carefully helps predict its future orbit and will also help model the future movement of other asteroids. Like, is this something that needs to be moved, or is the orbit going to diverge from what we predict? That sort of thing.
And then, Ivan, I understand there's also the opportunity to look at this asteroid as a potential resource for the future?
Scientists have said to me, realistically, this is probably a 22nd century kind of purpose, but we're at the beginning of assessing what raw materials are out there in the solar system. And in a future time, if humans expand further and make more use of materials that are out there, this is the beginning of our kind of assessment or reconnaissance of what asteroids are made of and how they might be used in the future.
So like asteroid mining, essentially, is what you're talking about.
Asteroid mining, for water or for minerals or for other raw materials. I mean, it's basically just knowing what's out there. And at some point in the future, that might be useful.
Okay, so that's kind of the reason why we're doing this. Let's actually talk about how we did this then, Ivan. So the Osiris-REx spacecraft was in space for 7 years before the sample returned to Earth. Can you just explain the process? Like once it got to the asteroid, what did it have to do in order to collect the sample?
It's a really interesting story, and this is actually where Canada comes into the story as well. Canada provided one of the instruments on the spacecraft called OLA, which is the Osiris-REx laser altimeter. It's basically a laser that you can almost imagine a scanner, like you would scan, like a printing scanner or something like that. But what it's doing is it's scanning the surface of the asteroid very rapidly with the laser to kind of build up a 3D model of the surface. The spacecraft also has cameras looking at the asteroid closely, and so basically when the mission was launched in 2016, it arrived at the asteroid Bennu in 2018 and started to go into orbit around this very small body. So that's when the scanning really began in earnest and the high-resolution photography. And the point was to try to find a location where it might be safe enough to bring in the spacecraft to snatch a sample. Now, the wrinkle was that the asteroid was... I think scientists admit that they were expecting something more powdery. You can imagine almost like snow drifts of fine material covering a surface. Instead, the asteroid was just wall-to-wall boulders. As one scientist said to me, it's almost like it was trying not to be sampled. It was so difficult to find a place to kind of sneak in the spacecraft. But they did manage to sneak in and make contact. There's a metaphor I have in mind. I sort of think of it like... it's a delicate maneuver. I think of it almost like if you're on a canoe trip and, say you're coming into a portage with your canoe and there's lots of rocks right at the portage and you're trying to kind of, how do I bring in the canoe without banging it into some of these rocks?
Such a great Canadian analogy. I love it.
Exactly. How do I get, and so the Canadian laser mapping obviously helped with that. And then the spacecraft successfully was able to pull away. But then it's basically been another 3 years to get back to Earth and for that sample to finally arrive.
We'll be back in a minute. So now this capsule with the sample is back on Earth. Tell us again, how much was collected and what did we get?
Well, the estimate right now, it's hard to say for sure. The estimate that scientists made before the return was about 250 grams, which was a mission success from their point of view. The requirement for the mission was to get at least 60. Of whatever they've got, 4% of it will go to Canada ultimately. So Canada gets a 4% share sort of as a national asset eventually. But meanwhile, the science team will be looking at the sample, looking to see how heterogeneous or homogeneous it is, what's in it, and a whole battery of different analyses will take place.
Wow. Why was it so important to grab the sample from an asteroid in space, right? Because, of course, we have meteorites on Earth. They land here fairly frequently. They're small chunks of asteroids that have made it down to Earth. So why can't we just study those and learn the same thing?
Well, those meteorites are falling all the time, and they are being studied. That's true. And occasionally we get really lucky. There was a case about 20 years ago, the Tagish Lake meteorite that landed in northern BC. In January, meteorite, a very fragile carbonaceous meteorite, broke up over a frozen lake in northern BC. So people were able to go out in their snowmobiles and scoop up this material in the snow, put it in freezers, and you could, actually study it. But mostly that's not what happens. Mostly they burn up in the atmosphere, or if they make it to the surface, they're highly altered by the heat. And then they're contaminated as soon as they get to the surface because, you analyze those objects, but you can never be quite sure, especially with organic material, is this something that the asteroid or that the meteorite brought in, or is this something that it picked up as soon as it got to the ground? And some meteorite material, it's the kind of more metallic, stony meteorites that have a better chance of surviving it to the ground. Ones like, pieces of Bennu, which would be very brittle, friable, and probably very easy to break up and pulverize, you can imagine that material wouldn't survive very well as a meteorite. So this gets us a pristine sample, a more representative sample, and as soon as that capsule arrived and they, airlifted it over to a temporary clean room, they got into a nitrogen environment. It's currently sitting in a box at the Johnson Space Center now in a nitrogen environment. So it's separated from oxygen. So all the chemical reactions that start happening when you have oxygen in the environment, it's kept safe from that as well. So for all of those reasons, it gives you a really pristine sample, and you don't have to worry about how it might have been affected by Earth's environment.
Okay. And it sounds like they've taken a lot of steps here to make sure that this sample from Bennu is going to stay very pristine until they want to open it up and actually take a look at it.
Right. I mean, the best possible scenario would be to go to the asteroid and do all the research there, except that the lab equipment would be too heavy. The stuff you really want to do would be too heavy, too impractical to try to bring all that to an asteroid. And of course, as you're working, you might think of more things to do with it. So you want to have it on Earth where you have access to all the equipment, all the possible techniques, but somehow you want to keep the sample as though it's still in space. And that's what they're trying to do.
And so if we've got a 250 gram sample that was returned in total, so that's about a cup, I think, right? So
exactly.
And we get 4% of that. So I mean, that seems really small, though. Like, can we actually do stuff with that?
There's a lot that you can do with it at a small level. I mean, the thing is, a lot of this thing will be almost in a powder form. In fact, already there's a picture of the open capsule, the open lid of the capsule this week, and you could sort of see this rim of black powder around the opening. So some of the fine dust will be very small indeed, but even those little grains of dust will reveal lots about the chemical makeup and about some of the physical properties. There will probably be some surprises, and for the Canadian sample, the idea is that whatever Canada gets will be representative of the diversity of the whole sample. One thing that everyone is curious about are organic molecules. These are molecules, not living molecules, but kind of precursors to life, molecules that have a lot of carbon, maybe like long chains of carbon, for example, molecules that could be, on an early Earth could sort of be some of the raw materials that would have allowed life to begin. So there's a lot of curiosity about how far that process could get on an asteroid.
Wow. So, I mean, it sounds like we're looking to this to, help us understand the big questions here of how life started or where materials came from potentially that were on Earth to start life.
Yeah, it's one of those things like the formation of the solar system is sketched out in approximate form. We sort of have a rough idea of how the planets formed, and we can look out, using big telescopes, look out and see solar systems forming elsewhere that kind of conforms to that picture. But the details are really fuzzy. So I think all of these clues, getting at these really fine details of, okay, what was the solar system made of? What was the influence of the early sun? And I mean, our solar system was made of stuff that came from other stars at some previous generation. What's the residual material that came from an earlier time that might be found? So all of these help fill in the gaps and really make that picture much clearer.
Could this potentially also tell us about anything about life in other places potentially? Like if there is anything else out there?
I think it could be quite interesting to see what those organic molecules are like, because we know on Earth life emerged fairly quickly. There's geochemical evidence that there was life on Earth at a very early stage. Now, this would have been microscopic life, and it took a long, long time before it got beyond that. But that kind of raises this question, because it makes it seem like life is pretty easy. Almost as soon as Earth had a stable surface, there were bacteria or something like that. And you wonder, is that happening elsewhere? So looking at these raw materials might help address that question, or at least kind of give additional information. So it gets at that question, the deeper question of astrobiology, which is how common is life in the universe and how enduring. And so one way is to look out deep into space and look for signs of habitable planets, but another way is to look at the history of our own solar system and see what we can learn about how it happened here.
Fascinating. Wow. So now, Ivan, we've got this sample. How long will it take for them to study it, and when will we actually learn what it contains?
Yeah, the first portioning out of some samples could happen, as early as the next few weeks. It depends a little bit on how quickly they can fully capture and understand everything they've got, and then, as they say, containerize it so they can put it into separate containers and send it off to different places where people can do different experiments. And of course, there will be things done right there as well at Johnson Space Center. So we might start to see things happening in a matter of weeks, and certainly in the next few months, I'm sure we'll have some of that material coming to Canada as well. In addition to that 4% that I mentioned that Canada gets, there are Canadians on the science team who will have some early access to the sample. So there are at least 4 labs in Canada, in Vancouver, Calgary, Winnipeg, and Toronto, where probably in the next few months they will be working on some of the sample material.
Wow, fascinating. And we might come back to you, Ivan, when we finally do know what that contains. Thank you so much, Ivan, for taking the time to speak with me today.
My pleasure. It's exciting stuff.
That's it for today. I'm Menaka Raman-Wilms. Our producers are Madeline White, Cheryl Sutherland, and Rachel Levy-McLaughlin. David Crosby edits the show. Adrian Chung is our senior producer, and Angela Pacenza is our executive editor. Thanks so much for listening, and I'll talk to you next week.